Now, several. By the way, you agree that this long division algorithm is really quite complicated. Yes? It's sophisticated. Very sophisticated. Now think about it. The guy who has invented this is very good. I don't know who did. It's quite recent, 6th, 7th century maybe. But it's quite good. He had to be very good. Oh, here's it. Right? So it's worth studying. When you finally understand it, I hope you admire it. Do you? Let's put the clicker. No. You should. I mean, this is extremely ingenious. Okay. Now, there's several supplementary remarks I want to make. One is that that's something I don't want to pick up because you probably not going to appreciate it, and I don't want to take the time doing it. And of course, it suits my conscience that even if I don't do it, I can say you can read it in the book. The following fact. Oh, I erased it, sorry. Again. It's something you should know, but as I said, probably not at this juncture. Okay, so now you notice what I said, what I've been saying all along. You want a single digit at a time, right? And this is exactly what we've done. We got that, we got that, and we got that. Now, of course, both of us were too busy doing so many things. We didn't pay attention to one critical element. I said I want a single digit. Now, don't forget, at each, oh yeah, here we go, still have it. Here, look at this. Yes. You will have this, you will have this, you will have this. Well, of course, it always works out to be single digit. This is, don't forget, what is this? This is the quotient of a particular division with remainder. This is 27, right? Divided by 6. And you want to see what the quotient is, what the remainder is. This is 39 divided by 6. You want to see what the... So. How do you know that you always have a single digit quotient? That's assumed. Because if that is not true, my whole the conception of the algorithm falls apart. Correct? Don't forget, right? I said, take one digit, take another digit, take another digit, one at a time. What if suddenly you say, oh, here is 12 rather than 4? Then what I'm doing makes no sense. In other words, I've completely broken my promise. Yes?
Put the remainder of 3 at the very bottom.
Oh, 3, sorry. But it's a matter of fact, you can completely prove the fact that with this kind of division with remainder, it's always single digit. I can give you one quick explanation. For example, why is that 27 divided by 6 would be one of a single digit quotient? Think about it. How do you get 27 again? 27 is what? You take the remainder multiplied by 10 and add to the next digit, right? Now, suppose this remainder, now you're dividing by 6, right? Supposing this remainder were 8. There would be 87. What would the quotient be? Like 12? But it cannot be 8. Cannot be 7. Cannot be 6. It can be up to 5. That's it. Because the divisor is always 6. There's always less than 6. 10 times it is either 50 or 40 or whatever. You add a single digit, that means it never climbs up to 60, does it? Let me repeat, right? This is never as big as 6. 1, 2, 3, 4, 5. 10 times it is there something either 50, 40, 30, 20, 10. Therefore, when you add a single digit number, right, 50, add anything you want, short of a single digit, it never goes up to 60. If it's not as big as 60, the quotient cannot be 2 digits. See, that's the reason. Right, so, in fact, I've explained it to you already. But if you can prove it precisely in under all circumstances and so on. Yeah, so, never mind what I said, but you understand that there's an issue. All right? So most likely, if I'll guess you, I'll bet you 5,000 to 1 that when you do this, you explain it, no student would ask you that, how come each time you only get a single digit as your quotient? But in case, in the rare event that someone smart enough to ask you, you're ready. All right? Okay. Now the third thing I want to point out to you is that, I keep emphasizing, all these algorithms are completely place value independent. That's the paradox, right? I'll repeat what the paradox is. The reason for the correctness of the algorithm is completely dependent on the place value. Look at this. You start with the expanded form. What is expanded form? The expanded form is the naked display of place value. So the whole argument at the end, look at this. What is this? Place value. 1, 4, 6, 100th place, 10th place, single 1st place. Yet the algorithm, if it's an algorithm, you don't expect the machine to read a digit and say, oh, this is stands for 5,000, or maybe it's only 500. It's 5,000, and I as a machine must do something different. If this is only 500, I as a machine will do something entirely different. You can't do that. A procedure is a procedure. It's a machine procedure. It's completely objective. There's no value judgment, whatever it is. You have a single digit is treated as single digit. That's it. Right, so now let me display to you, in this case, in what sense it's independent. Now, okay, I divide, look at division with remainder of, like this. I go through the motion. That's whole division. Correct?
Don't forget the 0.
No. I don't know. It's a 0, so then,
You on top of the 5?
Up of the 5?
Yeah.
Oh, sorry. Right.
Sticker.
No, yeah, okay, right. Oh, yeah. All right. Now look. Do you see any difference in here? Okay. Any difference? What is 7 here? What does 7 stand for? 7. What does 7 stand for? Does it make any difference? Of course not. That's the whole point. So you have to, the algorithm has to ignore place value. Contrary to what people tell you, that whatever you do, keep in mind place value. That's a different story. Yes, you must know that. But there comes a time when that obstructs thinking. You don't want to have anything to do with that because you work hard, which is like this. You work hard enough using place value. At this point, you can forget it. And that's why the algorithms are useful, because by ignoring so many things, you achieve simplicity, right? How do you achieve simplicity? You can only do that by ignoring many things. And the whole purpose of this is to work so hard using everything at your disposal, you come to a place where you say, I can rest. That's what mathematics does all the time. You work very hard, and at a certain point, something can be used with no thoughts attached. Just use it as mechanically. That's mathematics. Now, I'm going to emphasize this point again and again because the fluency in the execution of skill is of paramount importance in mathematics. But you should do lots of things without thinking. Otherwise, we're not going to get anywhere. On the other hand, why do you deserve to do things without thinking? Well, you achieve that status by thinking a lot first. So that dichotomy you cannot ignore. I mean, the prevailing dogma tells you, you must think every step, because otherwise you're doing things by rote. Therefore, you have no conceptual understanding. Such a statement can only come from people who know nothing about mathematics. That's the point.